what I tell my students is we always need to validate our CFD results, because when you run a simulation, you always get a result, right? And there's so many parameters that go into the software that we just can get our wide range of different results, and we need to make sure that we're using the correct parameters. So this presentation is actually based on the PhD dissertation of a student of mine, Giancarlo Cherubin, who did his PhD in Brazil at the University of São Paulo, co-mentored by Richard Vogels. So the presentation has two parts. The first part I'll talk about comparison of CFD and physical models in the context of nasal resistance, or the pressure flow curve. And then the second part is a comparison of CFD with rhinomanometry. So let's go to the first part. So we created this plastic replicas of 6 individuals. One was a healthy patient, and 5 were patients with nasal airway obstruction, who, as you'll see in a minute here, because we also wanted to compare with rhinomanometry, we used decongestion with oxymetazoline just to get rid of the effect of the nasal cycle, because there's a gap in time between acquiring the CT scans and on which the CFD is based and getting the rhinomanometry performed, right? So the decongestion was important to make sure that the nasal airway was the same on the CT scan and the rhinomanometry. So the models were 3D printed, and this is the experimental setup. Fairly simple. We tried to reproduce an in vitro rhinomanometry. So one nostril was blocked with tape, and then we inserted this catheter through the tape, sealed it as much as we could, and so that catheter provides the pressure measurement right after the nostril, which reflects the pressure at the back of the nose after the septum, right? And then we used laboratory vacuum to suck air through the model. And this was performed separately for the left and the right cavities. So we have unilateral nasal resistance, and we measure the flow rate with this flow meter here. Then we use the exact same geometry for CFD simulations. So we use tetrahedral meshes with 7 million elements. And we used, I would say, simple simulations on commercial software, ANSYS Fluent, using both the laminar model and the standard K-omega turbulence model. So these are the results here for one patient, or the healthy subject, for the left and the right cavities. You can see generally a good agreement for the flow pressure curve, comparing the experiment with both simulations. The laminar simulations tended to predict flow rates that were a little higher than the K-omega, mainly for the higher flow rate. So of course, as you transition into turbulent flow, the K-omega is more accurate. So now these are the 5 patients with nasal airway obstruction. So we tried to select a range of patients with different levels of nasal resistance, just to have different ranges of patients. You can see that our CFD methods provide a better results for some models versus other models. So this is now just comparing the K-omega results with the experimental measurements. So to compare more precisely nasal resistance, what we did is, because this was all done steady state, right? So it was a constant pressure drop, and then we measured the flow rate. And so both for the CFD simulations and for the in vitro measurements, we fitted a power law curve, which provides these coefficients A and B. And then once we have the coefficients A and B, we can compute the entire curve and have the pressure drop and the flow rate at specific points. So in the rhinomanometry literature, oftentimes resistance is reported at two pressure drops, 75 Pascal and 150 Pascal. So that's how we obtain the exact values at 75 or 150 Pascal. And then we compared resistance measured by CFD versus resistance measured in vitro. So for both the laminar and the turbulent simulations, and for both 75 and 150 Pascals. So here you can see that there was a pretty good correlation between the CFD nasal resistance and the in vitro nasal resistance. We define the accuracy of CFD as the ratio of the nasal resistance measured by CFD to the nasal resistance measured experimentally. And here you can see that the accuracy we got ranged from let's say 90% to 95%. So the K omega model was a little more accurate than the laminar model. But still, I mean, of course, from a basic science perspective, we'd like to have like 100% accuracy, like they get the exact same result. I think from the clinical perspective, clinicians are probably more interested in saying, oh, if you reduce the nasal resistance by 50% in this patient, how can I accomplish that? And I think the methods we used are probably accurate enough to have these relative changes from or comparisons between one patient and another patient. Okay, so now part two, rhinomanometry versus CFD. So Dr. Querubim in Brazil recruited 25 patients with nasal airway obstruction. So this is the sample here, 15 females, 10 males, age on average of 35-year-olds, body mass of 73, and a BMI of 27. You can see that there's a range in the pre-surgery nasal nose score of 75, which is pretty typical for a surgical patient. So this is what the CTs look like with the decongestion. For us who usually do CFD mostly on non-decongested patients, the airways look really wide open, right? So the CT was performed about 1 hour to 1.5 hours after applying the nasal spray. So the literature we found says that it takes about 30 minutes for full effect of the nasal spray. And then once that effect is achieved, the airways, the mucosa remains decongested for about 4 hours. So we have this window of time that the airways were stable. Then rhinomanometry was performed about half an hour after the CT. So this is actually the main author here, Dr. Querubim. So showing how the rhinomanometry was performed. And for the CFD, we reproduced the rhinomanometry. We had this air ball in the front to have the inlet boundary conditions. And we closed one nostril at a time so that the flow be unilateral. And so here is a comparison on one patient. So one interesting point is that I'm not an expert on rhinomanometry. We have here a real expert on rhinomanometry, Dr. Fogg. Rhinomanometry on our hands had a lot of variability. So between different tests, we had different results. But nevertheless, our CFD results tended to overestimate the flow rate or underestimate the pressure for a given flow rate. And to compare CFD with rhinomanometry, we chose this pressure drop of 75 Pascal. So in the traditional rhinomanometry literature, they recommend 150 Pascal pressure difference, but we find that patients often have a hard time reaching 150 Pascal, so we chose 75 Pascal. So now this is a comparison of nasal, the flow rate at 75 Pascal measured by CFD versus the flow rate at 75 Pascal measured by rhinomanometry. You see there's a lot of dispersion. On one hand, we're happy to see there was a statistically significant correlation with an R squared of 0.58. On the other hand, we can't really say that the CFD simulations in one specific patient accurately reproduce the nasal resistance measured by rhinomanometry in that specific patient. So using that same definition of accuracy that we had for the in vitro experiments, where we had the CFD accuracy being from 90 to 95%, now for rhinomanometry, the CFD predicted nasal resistance was only about 65% of the rhinomanometry measurements. And you can see that the standard deviation is pretty large. Okay, so potential reasons for the discrepancy. So in my earlier presentation this morning, I mentioned that the segmentation threshold has a major impact on the resistance. So I don't know exactly what is the optimal segmentation threshold to get the same resistance as the patient. Typically, we use minus 300 because that's the easiest one to do a quick job because it gets rid of a lot of artifacts. But the analysis we did, it sounds like if we use like a smaller range of like maybe minus 800 Hounsfield units, that would provide a higher resistance that would be more comparable with the patients, at least the rhinomanometry measurements. The second possibility is this assumption of a rigid nose. So when you ask patients to use the rhinomanometry, they really need to do the strong sniffing that leads to more collapsibility of the nasal valve that, of course, CFD didn't reproduce here. And then I didn't list there, but we have a lot of experimental variability with rhinomanometry as well. So it's like on one hand, rhinomanometry is the gold standard, but on the other hand, it also has a lot of variability, right? So the other large study I'm aware of that has done a similar analysis was performed by Zhao and Jiang in 2014, where they did a similar analysis for 22 healthy subjects. And they also found a statistically significant correlation. Their R2 was a little smaller than ours. On the other hand, they did something different from what we did. So they compared nasal resistance measured with rhinomanometry at 75 Pascal, which is what we did. But they did CFD with a pressure drop at 15 Pascal. So when you look at the table in their paper, the numerical values of resistance are very similar in rhinomanometry and CFD, but they are really measured at different pressure drops for rhinomanometry and CFD. Okay, so in conclusion, we find that CFD reproduces fairly well nasal resistance measured in vitro in a plastic model. But when we compare it to rhinomanometry, we get lower resistance values and more variability. And so one future direction is to try to understand why the correlation of CFD and rhinomanometry wasn't as high as I hoped for. Thank you.